Conference. It's my great pleasure to introduce Professor Robinson from University College London, and also he is also at LCN, London Center for Nanotechnology. And Ian will tell us today also is related to the previous course, mechanic properties. This is a mechanic breakdown of band silicon nanowires. And let's thank our speaker.
Well, thank you, and thank you for the kind introduction and also for the invitation to come here. I'm going to regulate the microphone by distance. It's a little bit of a difficult microphone. I'll take this off. Is that a little bit better?
Yes.
All right. So it's a pleasure to be in Hong Kong again and have a nice long slot to tell you about some of these results. What I'm going to do is, I've lost his name off the bottom here. These are the primary co-authors that are involved in the work that I'm going to talk about. It's a sort of related topic to the one we just heard about, using X-ray diffraction to look at strain distributions in silicon structures. We're going to use the slightly different technique of coherent X-ray diffraction, which I will need to introduce a little bit because it's still a relatively new technique. But one of the things I want to get across is that this is wide open for business, and so if you know people that have got devices that would be interesting to look at, where the strain distributions are interesting, we would be very interested in using our method to work on these. I will also take the opportunity as I go along to I've got quite a few examples in here, and I will use those examples as potential collaboration points with some of the theorists in the audience. So I'll point out where calculations would be interesting to be made, and please feel free to interrupt with questions if you have any. But I will try to make the connection with potential future collaborations. So. Jesse and Marcus were postdocs with me. Ross was a postdoc and is now in charge of the beamline at Argonne National Lab, where some of the experiments were done. Others were done at the Diamond Synchrotron in UK. Lauren and Xiaowen were students that were involved in the project at different times. And the name that's gone missing is Gang Xiong, whose work this really is mostly aligned with. Because he's just finished his postdoc for 4 years in the LCN, entirely working on this kind of problem. And so he's the one who's made all the devices that we've been looking at. And it's mostly his work that I'm going to be talking about. The work was supported by a 5-year grant from the European Research Council that I'm very grateful to have received. We're just coming to the end of it, so this is a nice summary account of some of the things that we've been able to do with that grant. So the topics I'll try to cover in an hour and a half. I've got quite a few different topics to look at. I'll be brief on the introduction to do with strain-engineered semiconductors, because Connell has just given a very good account of how the strains act. I'll just make a couple of additional points on that. And then talk about the coherent diffraction imaging method. And the particular message that I want to get across is that the strain gets mapped as a complex density function. And I'll spend a bit of time explaining that and illustrating it, because it's a little bit difficult to understand the results if you don't get the point about the strain. And then I'll use it to look at a few different relevant materials. So we've been doing some work on semiconductor nanowires, and show you how far we've got with that. We've been doing work looking at lattice defects, and this is particularly important when we get to the sort of very miniaturized level of very small semiconductor components. We've also done some work on SOI type materials, and I've got some potentially interesting results there to look at that might be interesting to model theoretically. And then at the end, I'll talk about the future a little bit, the possibility of doing ultra-fast experiments. It's not necessarily a good method to look at semiconductors, but it could be, and so we'll talk about it perhaps. And if time allows, I'll just talk a little bit more generally about the possibility of using free electron laser type sources for material science applications. Okay, so here are some taken from a not so recent IBM review. This is some of the technologies that are being talked about with current designs of transistors. So we've just met in Colin's talk, we've just met the FinFET, which is a way of solving the short channel effect problem, where you can concentrate your gate into a particularly small area and not have the depletion effects that take place around it. SOI, I think we're pretty familiar with the idea that you can avoid the capacitance losses associated with the depth of the silicon by using a silicon slab on an insulator layer. And a variation of that that's discussed in this review article is ultra-thin SOI, which again goes further in that direction. Not mentioned here, but I will talk about is the idea of pre-stressing the SOI, and we'll look at some of the effects of that in some of the examples that I'll show. So at the bottom are cross-sectional SEM pictures that have been colored to show the different regions in a real actual device for the three examples. I have another example here. And this is showing the SOI method where you put in an oxide layer and pattern your material, your channel, into an already thin silicon layer, which is wafer bonded onto the substrate, and then you put in your stressing structure above with the gate sitting above the device, or the more conventional standard MOSFET configuration with the stressing arrangement, and then the FinFET once more. This is looking at the questions, a different review article, that again showing some of the configurations that are involved. None of these is labeled with the dimensions, but we are talking about getting in the 22 nanometer technology, we're talking about getting channel lengths of the order of 20 nanometers, and this is where the gate starts to become a problem. But there is also the question of whether it's better to use biaxial stress by using an epitaxial layer that would be grown in here, or one of the methods, for example, that's illustrated here to get tensile stress is to use a buffer layer of silicon germanium and then grow the silicon on top of it so that it will get a biaxial stress in the tensile direction. And as was just explained, that's the direction that improves the mobility for NFETs. And so when you go into a CMOS technology, you need an NFET next to a PFET, and you need to stress these in opposite directions, as explained, because of the piezo-resistance coefficients. And that can be done by using different materials for the stressor structures, which are built on top of the devices. So this would be a way of applying a uniaxial stress, because the stressor structure is a cylindrical structure that runs along the entire channel, and so stress is only in the direction in the plane of the screen that's seen here. Okay, here are examples of those. One more idea. This is actually a very interesting idea that has obviously been put into actual production because there's a real image of it here. I haven't found any other references to it being used, and maybe somebody here does know if this is a viable technology or not, but it's called a hybrid orientation technology, and that is to use a silicon 110 substrate, which will be the handle of the chip and the device, and to put an SOI there, which is 100 oriented, and then to make the NFETs in the SOI layer, so that you would pattern these into the thin layer of silicon here with the appropriate stressor, but then to put the PFETs into the 110 material, which is the one where the effective mass can be tailored by stressing the device more effectively, because the piezo coefficient is more favorable for 110 oriented silicon to make the improved hole mobility that's needed for the PFET. So you can make a CMOS device with a gap in the middle where the N and the P components are side by side, but they're actually on different pieces of silicon inside the device. Okay, so this is just a brief mention of the band structure effects that are involved. What we're looking at is the valence band minima, which are in silicon distributed in the 100 directions, and the effective mass, of course, is the inverse of the curvature of these bands. And the one that gets modified by the uniaxial strain is the one in the direction that you perform the strain. And the idea is that you would be able to, this is shown for the 110 orientation, but you would be able to actually use the band which this is shown for the whole orientation, but you would use the top of the conduction band whole state, which is the one that gets its effective mass modified by the strain that you introduce. Okay, so that's the kind of applications that we're looking for in the semiconductor devices. And what I'm going to focus on is the measurement of the strains that would apply to the materials that are fabricated in devices such as this, with the dimensions in the range of nanometers. And I won't be able to show you results on the nanometer scale. We've been looking at devices in the hundreds of nanometer scale, which is more practical for the measurement, but the results that we get can be extrapolated down to the current technology scale. There was the question after Connell's talk just now about whether you can look at these in situ with currents flowing in them, and the answer is yes. You can, if you use X-ray methods, you can do this, but for a couple of caveats. One of them is that the samples are damaged by the X-rays, and so the electrical properties might not be valid when the X-ray measurement is being made. We've tried to do some experiments like that on nanowires, where we've had arrays of nanowires connected up on a chip, and we've been able to put current through the wires, and we've been able to put X-rays on the wires and measure the structure of the wires. But so far we haven't been able to do both at the same time, so we don't quite have the answer to the question yet, but we're close, and we're going to work in that direction in the future. Okay. So what I'll discuss before I show the coherent diffraction method itself is the kind of things that one would expect to see changing as you make the devices smaller and smaller. And the first thing that will change is that because a small structure of silicon will have more surface area, there will be a renormalization just of its lattice constant that will come about just due to the fact that there are surfaces present. This is illustrated This is for metal particles, but it shows measurements of the lattice constant of powders of nanoparticles measured by Littinai's group in Stuttgart, where the change of lattice constant of the particle, just measured by the position of the Bragg peak with X-ray diffraction, is plotted versus the reciprocal of the dimension of the particles. And you could imagine this would apply to blocks of silicon as well, but the measurement just hasn't been done. And what you find is a linear behavior, and the linear behavior can be understood fairly well. In this case, the particles are assumed to be spherical, and a spherical particle with a surface stress on it, which is represented by this symbol here, will have a pressure difference across it due to the fact that it's got a curved surface. And the pressure difference is equal to the stress divided by the radius, so it can be converted into the diameter. And the response in the lattice constant with a couple of geometric factors is just given by the bulk modulus. So the only symbols that appear in this equation that gives the straight line that fits the data are which is the linear relationship with 1 over the size of the particles, contains a measure of the surface stress, which turns out to be 2 newtons per meter, which is a typical number for a surface stress, and the known bulk modulus of the material, and that gives a good straight line. So this shows that small particles will undergo a contraction just due to the surface tension, surface stress, which is surrounding them. And again, for small particles, that will show up as if you have a typical situation where you get the equilibrium crystal shape, you get some flat regions and some curved regions in general in the equilibrium of some small object. And the curved regions will have a pressure difference across them due to this, due to the surface stress, but acting through the Gibbs-Thompson effect. That will give a pressure difference, which will give a compression of the material inside the curved region. And to anticipate the readout that I'm going to be talking about later on, that would correspond to a phase shift of 0.6 radians, but we'll see a little bit later where that comes from. Okay, so if we talk about ways to image these, there's quite a few interesting and potentially important methods of using X-rays to image materials. And many of these are still under development, and I'm only going to talk about a couple of them today, but I will review the full sheet of them just to show you the sort of things that are available. The most boring and most interesting is just to shine the X-ray straight through the sample and just image what comes out the other side, and you can get absorption contrast. And I think I've got these in order. And that's a 100-year-old experiment that is just showing that you can X-ray things and see what's inside them. But looking at nanoscale materials, you're limited by the detector, and this method just doesn't really work. But if you use diffraction, then you would use this method of X-ray topography. Colin just mentioned it. I'm just mentioning it. I'm not actually using it, but we can also, that's the next example. You can also use it to see, these are not nano objects, these are micron-sized objects, which are defects in it's a semiconductor material, but this is gallium nitride, I think, that's looked at here. And you can get topographic contrast corresponding to the strains in the material by using a Bragg peak to look at it. Okay, so the second method that you can use is to measure, you shine the X-rays onto the sample, and instead of measuring just what comes straight through, you measure the diffraction pattern that comes out of the other side. And this diffraction pattern can be inverted by using the fact that it can be measured more finely than the fringe spacing of the diffraction pattern. And the famous example that really opened up this whole field of diffraction imaging is the one of John Yao that was published in 1999. So it's very much a 21st century technique that is becoming available. And this one, unlike the first method, requires the coherence of the source in order for it to work That also converts into a diffraction version. This would be a Bragg diffraction version where you look at the Bragg peaks coming from the sample that you're looking at. You measure them with a finely spaced detector far enough away that you can oversample the diffraction pattern. And by the same analysis method, you can get images of the sample with the additional possibility of measuring strain. And this is the method I'm going to concentrate on most today because it's the one that I've been using the most. And that one, it's an older example, but this is showing a strained, distorted image of lead small particle. I think it was 500 nanometers in diameter. There's also lens-based imaging methods which are very much under development and not really quite ready to talk about or apply in this situation. So we're going to focus on this one. But just to complete the picture, the lens-based imaging is where you put a lens between your sample and the detector, and then you can turn the scattered X-ray beams coming from it into an image. And that rather dark, but that's an optical bandgap material that's been imaged by that method. And then finally, that can also be done with diffraction as well. And you get images which have got phase contrast. Here it's corresponding, again, it's a little bit dark, but these are steps on the surface that have been imaged by Paul Fenton's group photography. Okay, so here is an aerial photograph of the diamond light source. The imaging beam lines are all concentrated around this part of the ring. You'll see that only one of them has been built when the satellite flew over for Google Earth, or whoever took this picture that I downloaded. I-13 is the one over here. That one is now has been operating for about 1 year, and that's the one where I'm doing most of the experiments today. I-14 has just broken ground, and they're just starting to build it right now. So this will be ready in about 3 more years' time. But we're open for business on I-13 for doing this kind of experiment. It also shows the research complex, which is where my research group is now located. We're using the labs here to prepare the samples that we measure over time, and so we've got a very nice relationship with the 2 buildings next door to each other. And what gives us the coherence is the development of the X-ray undulator. This started in Russia in the 1970s and has led to the 3rd generation of synchrotrons, of which there are now a dozen in the world. The closest one to here, I think, is probably Shanghai synchrotron, or okay, somebody's nodding. But there is quite a few of these facilities in the world, and I would say it's pretty safe to say that you need the undulator technology of the 3rd generation in order to have enough coherent flux to do any of these experiments, and the previous generation just didn't allow it. I mean, only just could you do some experiments before that. Diamond's particular version of this is to go in vacuum to get very small gaps and to really improve the performance of the undulator, but this is now becoming fairly widespread technology that's available. Okay, so our experiment is actually pretty simple. We just need a coherent beam, so we have to throw away most of the beam from even the 3rd generation sources. This is a big waste, but the source is only about 1% coherent, and so we throw away 99% of it. In the not too distant future, the sources are going to be upgraded, starting with the SRF in Grenoble and then hopefully at Argonne as well. And they will be able to get up to, for hard X-rays, up to about 50% coherence. And so this will be an enormous improvement to the experiments coming along down the road. But right now we work at about 1%. We take out one coherent mode from the source, and we put it on the sample and measure the diffraction pattern. And because it's coherent, we see interference coming from all of the extremities of the sample. And if we rotate the sample, we get a full 3-dimensional diffraction pattern, which is giving us complete information about the 3-dimensional structure of the sample. We're also able to put focusing optics in, so long as we put them in after we've put the aperture to define the coherence. And that gets us down to quite high fluxes on the sample, gets us to match the size of the beam to the size of the wires or the silicon structure that we're looking at, and use that 1% of the flux fairly efficiently. But that's the only optical trick that we're using. Otherwise, we're just doing a straight propagation to a faraway detector, which effectively measures the Fourier transform of the shape of the density function of the crystal, which is mainly the shape, but also, as I'll show, contains information about the strains inside it. Okay, so if you have a powdered sample, you would get a lot of powdered spots. You can pick out one of these. They would be arrayed in a Debye ring like this. You can pick out one of them, and you can see it's got fringes on it, and you can measure those fringes, and that is the coherent diffraction pattern of the crystal measured at that particular Bragg peak. And that's the thing that you then invert to get an image of the crystal and all of the strain inside it. When you do this for semiconductor devices, they're usually with a single orientation on a substrate, so you have to space them apart enough that you can shine the beam onto just one of them. So the focusing is particularly important, so that you can zoom in on just a single device that you would like to look at. But the method is exactly the same. You get one Bragg peak, and you would just measure that one Bragg peak, and then you can look at many devices in a lithographed sample if you wish, and they would all have the same orientation, but so you wouldn't get the powdering for those, but you can still do the experiment. Now, this is a very important step. I'm not going to spend a lot of time talking about it, but it is the algorithm that's used to convert that diffraction pattern into an image. And what it's based on is the Fourier transform relationship. It's a three-dimensional Fourier transform between the shape of the object and all of the internal structure of the object and the diffraction pattern that you measure, which is this array of fringes that surrounds a Bragg peak in the diffraction pattern of the sample. And since it's a Fourier transform, you can just take the inverse Fourier transform, except for the not small problem that this is a complex function. You only measure the amplitude of it because you measure the intensity of the diffraction on the detector. You can't measure the phase of it, at least not easily. And so you have to use a bootstrap method to get the phase for the missing part of this diffraction pattern. But because you have additional information here, you've got more measurement points than you have information in the pattern. And that's seen by the fact that you have more than two pixels per fringe. So you're above the Shannon frequency of the information that's in this diffraction pattern. That means that you can use as a constraint in real space what's called a support, which is a mathematical box drawn around the sample, and you just say that the whole sample has to live inside that box, so you can use it as an algorithm step by just deleting everything outside it. So the real space part of the algorithm is to take the iterate that you would have of the image of the three-dimensional particle, cut it off with this support, come back to real space, you get a diffraction pattern which is only correct to the extent that the object you started with is correct. You overwrite the amplitude with the measurement that comes from your instrument. You keep the phase, and then come back to real space again, and then go around in a circle. And with a few tricks invented by these authors here, you can get a quite efficient algorithm. And in fact, we trust this completely now, so we get quite good results. And it works for simple cases, and towards the end of the talk, I'll talk about a much more challenging example where the strain is very large, and that one needed some further developments of the algorithm that I'll mention at the time. But basically, this is the imaging part. This is the lens of the imaging experiment, where you measure the diffraction pattern and feed it to a computational algorithm, which acts as a lens and turns it into an image of the sample. Okay, here it is in action. This is for a silver nanoparticle. The support is the shaded box surrounding it. This is a movie showing the frames of the three-dimensional diffraction pattern. There's an isosurface of the diffraction pattern. This is an SEM picture of the surface of those samples that are being looked at. And here is a reconstruction. Sorry, there's a reconstruction. This is a reconstruction of a section through the phase of the reconstruction, which shows as you'll see in a moment, this is showing where the strain is inside the particle. This silver crystal does not have very much strain, so it's basically just a green constant phase. Here's another nanoparticle. This is a gold crystal. The diffraction pattern again shown as a movie going. This corresponds to a rocking curve, rocking the crystal by about 1 degree, and this shows an image of the gold crystal that comes out. This is about 200 nanometers across, and you can see it's got this nice faceted shape that is the growth shape of the gold crystal. And here's where the phase information appears. So we usually, it's quite difficult to view because it's a three-dimensional complex density function. The most useful information is very often to look at the surface of the sample, so you just make an isosurface rendering of it, and then color the isosurface according to the phase of the complex density which is inside there. And this is where the phase gets mapped, where the strain gets mapped onto the image. The arrows indicate the 111 directions of the facets of the crystal. And this is the connection between the strain and the phase. So the strain corresponds to a distortion of the crystal. So what we can think of is the crystal as having regions of the material distorted in some way by some displacement field, U here, and the X-rays diffracting from that distorted region are shifted in phase relative to the rest of the crystal by the two red pieces in this construction here. And if you add them together, it's just a vector sum of the incident and exit k vectors, and that vector difference is the q vector of the measurement, and you just get the phase quantitatively equal to the q vector projected onto the displacement field. So if you wanted to measure this displacement field everywhere inside the crystal, you will have to make at least 3 different Q measurements non-coplanar to get 3 different components of the U. And that can be done, and I'll show you an example of that in a few minutes. Okay, so the phase of the image of this piece of crystal tells you about the projection of its displacement. And whereas the image has a resolution of about 20 nanometers or so, typically we get, the phase has extremely high sensitivity to the distortions in the crystal, because as you can see from this picture, if you move the crystal by a whole unit cell, it's indistinguishable from the undistorted one, and you get a phase of 2 pi. So your range of phase from 0 to 2 pi for the image corresponds to 1 unit cell of displacement of the material, and unit cell is a fraction of a nanometer. So it's really quite sensitive. You can get measurements of distortions down in the picometer range by this method. But it also tells you exactly where the problem that I was referring to earlier comes about as well. Because if you have a distortion of more than 2 pi, it's indistinguishable from a distortion of 0. And so there is a wrapping kind of behavior that takes place. So if the distortions are too large, it actually becomes it is possible, but it becomes rather difficult computationally to extract those. So it's very good for looking at small strains, but not so good for looking at large ones. Anyway, so what we are able to do then is to get a color image of the distortions of the material, and it's completely unrelated to this this method here, which is polarized light, visible light microscopy. But it does make the very important point, which we will see later on, that the strain gets concentrated at corners in the structure, and we saw a nice example of that from the previous talk. But it also makes the point that the strains are relatively slow varying. So the idea that you have 20 nanometer spatial resolution for distortions which correspond to picometer level changes in the crystal is actually quite appropriate. And so you can see the slow varying phase that corresponds to the strain distribution inside the material rather well. Okay, so here's another example. This is it's an electronic material, barium titanate. What we're looking at in the experiments I'm about to show are nanocrystals of barium titanate. These are used in supercapacitors. The interesting behavior here that's the basis of the technology is that nanoparticle barium titanate has 3 times the dielectric constant of bulk barium titanate. And the reason for that is explained by this piece of work here, which is based on powder diffraction. But they're arguing that the inner part of the particle is tetragonal, which is the normal state of barium titanate at room temperature. But the surface has got a cubic phase present, and there's some sort of intermediate in between. But we view this in the coordinate system of the Bragg peak, which is, we're going to show an image of this measured by this method. Here we're seeing, again, it's the surface of one of these particles. It's roughly spherical shape. We're just looking at a single particle, 200 nanometers in diameter, and it's got a strong phase structure present. This is due to this the presence of some distorted shell of material, which is reverting to the cubic phase, perhaps, viewed with one of the peaks of the tetragonal phase inside, and so the distortion looks like a strain. And we've got quantitative mapping of that strain all over the skin, all over the bulk of the material, and it shows up most strongly at the surface as this rich pattern of phase, which is shown on a scale where blue is minus pi and red is pi. So we've got a full 2 pi variation of the phase. Okay, so since we've got quite a lot of material to go through here, I'm going to pause at this point and take some questions if anybody has any. This would be questions about the method that I've described. And I'm going to talk about the work we've been doing on nanowires right after this. But does anybody have any questions at this point? Otherwise, I'll race ahead.
Can I ask one?
Yeah.
This, at the first part, you talked about this Gibbs-Thompson relation,
Yes.
which is the delta P equal to
Yes.
surface tension
Yes.
R or something like
Yes.
that. And how did you convert this delta P into your lattice spacing?
By the bulk modulus. So bulk modulus. So the K in that equation was a bulk modulus. So what we're saying is that it's a spherical model, but spheres work for many situations. So if you have a spherical particle, then the radius of the sphere is the pressure difference that exists across between the inside and the outside. And so if you have a surface stress, then that stress will result in a pressure difference, and that will show up as a compression of the crystal. And the tighter the radius, the stronger the compression, and that was the effect that was seen. Yeah, and that's a sort of general sort of beginning introduction to how the lattice constant should change. Of course, silicon structures tend to be sort of rectangular, and so it would only be the curved corners that would show those stresses, but there should be strains associated with the edges of the material that would come from that effect when there's a presence of a surface stress. Any other questions? Okay. So for nanowires, we've got this a very nice method of growing wires called the vapor liquid solid method, which is where you use a catalyst drop and you do CVD, chemical vapor deposition of the material that you're trying to grow, and it dissolves in the catalyst, and when it becomes supersaturated, it forms a single crystal, and the single crystal is limited in size to the size of the drop that you've created. And so you can get linear growth of wire-like structures. And if you change the chemical vapor that's going into the synthesis, then you can change the composition of the wire. So you can make heterojunctions, and it's proposed, this is the work of Charlie Lieber at Harvard, that you can connect these up and make a whole technology based on nanowires. And this, to my knowledge, is not being pursued by IBM or Intel, but one day, Anyway, one of the advantages of using a wire-like format is that you've got the quantum confinement of the states. If you make silicon with dimensions in the range of 30 nanometers, the band gap goes from indirect to direct, and so you've got a significant band gap engineering from the finite size, and also from the intrinsic strains that would be present in these materials due to this Gibbs-Thompson effect that I talked about. So you can use nanowire format as a way of modifying the electronic band structure, but of course it would need to be developed for for beating conventional CMOS. And it's got quite a long way to go, of course. These are CVD-grown indium phosphide wires, and you can see we can get three-dimensional images of the wires, and they look just like SEM pictures. Of course, we get information about the interior of the wire because we've got a three-dimensional image. And the thing that was interesting here, because they do grow from a catalyst, and there is a sort of residual root that occurs on these samples, which is this end of the stick here. We were interested in whether there is a strain difference between the wire part and the root part, and the answer is a very slight one. So there's a very slight color gradient along the wire here, and no color gradient. Just a single color here. Possibly the center of the crystal has a little bit different strain from the edges, but anyway, it's not a particularly dramatic effect that we're seeing. But we do get this is a cross section through the structure, and we're seeing a mapping of the strain inside this nanowire from the coherent diffraction image. By the way, when you look at the images that I'll show, I do this in my head because I've been looking at these for so long, but just please ignore everything outside the wire. This is the phase of a complex number, which is 0. So it's just a random background, and don't be distracted by it. What we're looking at is the phase of the image inside the wire, which is relatively constant with a very slight gradient running along it in that direction.
Can you tell the magnitude of the gradient? Is it more strain-free towards the free edge?
We haven't really. It's really at the level of visibility. So I'm not going to really stress the point, but just my eye says that there is a little bit more gradient going out in that direction. This, by the way, is probably, well, we know from the SEM picture, this is not the end of the wire. This is just a missing piece of wire. So there is probably a stacking fault at this position, and there's more wire beyond it, but we don't see that because we're looking at just one bright piece of that wire. In fact, stacking faults are the next thing I wanted to talk about. These are gallium arsenide wires that are measured. And here, this is just showing the raw diffraction pattern of one of these wires. The little elliptical streak here is the Fourier transform of the cross-section of the wire itself. So the width of the wire is shown as the reciprocal of the extent of this diffraction pattern here. And what's very interesting is that there's a pseudo-random sequence of peaks which comes from the length of the wire that is being illuminated, and when we move the beam along the wire, we get a different distribution of these peaks. And we've been trying to develop a method to invert this so-called barcode pattern into an image, and the closest we've got is this work by Vincent, which is shown here. This is the diffraction pattern we're working with, and it's a one-dimensional diffraction pattern of a sequence of stacking faults in the wire. So the way we understand that is that well, two possible models, but we're pretty sure this is the correct one at the bottom. You have stacking faults which occur in, this is gallium arsenide, but it looks just like silicon. When you have a stacking fault in the vertical direction in the screen here, then the phase of the off-diagonal 111 reflection changes by 1/3 of 2 pi. And so you get a 1/3, 2/3, and 3/3 phase shift for every one of the stacking faults that's introduced along the length of the wire. So we imagine the wire to look something like this with 3 colors associated with it corresponding to 3 different registries of the stacking sequence. So the wire is 111, and we're measuring the 1 direction, and so we can actually distinguish these as phase shifts of the material through this method. And it's not the same as what you would get by light-dark kind of contrast that would correspond to a more traditional kind of barcode. And what Vincent has done here is model both kinds of stacking faults, and he's got a genetic algorithm that gives a relatively good agreement with the data, but unfortunately it's not a unique image. So what we've got here are stacking faults. This is showing several things at once. This is the model that is used to agree with the diffraction pattern of the one we were just looking at. This is this is an image of the diffraction pattern that was measured there, and this is another wire, but this is a TEM image that shows you can actually see the stacking faults inside the material. And here's another example showing a slightly better TEM image, where if you look at gallium arsenide nanowires, you can see that you get both the light-dark contrast. This corresponds to stacking faults. These are imaged by dark field TEM, where you look at just one Bragg peak, and that picks out just one of the 3 phase registries of the material, and it looks light and dark according to whether you have the reverse stacking sequence or not, and then the stacking fault appears as a local light-dark contrast. If you go 60 degrees away, you can measure the opposite contrast from the same wire. So you can do it rather nicely with TEM and see these stacking fault sequences. Now, as far as the electronic properties, these are quite common in grown nanowires. They're particularly common in indium arsenide, I believe. Gallium arsenide shows them quite strongly. Indium phosphide, as far as I know, does not show them. But these could be controlled if necessary, and so you could imagine making, if this was useful for band gap engineering, then you could possibly build a technology onto these faulted wires that grow by the VLS method. Okay, a different kind of nanowire. This is zinc oxide, and here we've used a vapor transport measurement method to grow crystals of zinc oxide. These are in the micron size range. They're just about handleable, and Marcus Newton, who did these experiments, was able to manipulate single wires onto a marked region of a silicon wafer. So if you strain your eyes, you can just see one wire at that position right next to a little scribed cross on a silicon wafer. There's a zoom of it, and you can definitely see it down here. So what we did was to use the fact that we can control the position of the X-ray beam to measure the diffraction pattern of this, but because it's isolated, we can turn it around and measure several different Bragg peaks all from the same wire. And so here the exercise is to measure the strain in all its different projections and get a full 3-dimensional image of the strain field. So here are the 6 Bragg peaks we measured, and those are the diffraction patterns that correspond to the 6 Bragg peaks. They all look pretty similar, but there are small differences between them that correspond to the strains. Obviously, we're seeing the same Fourier transform of the shape, and so most of the information in the diffraction pattern looks the same, but the small differences come from the fact that they have the strains are not identical. So these show X, Y, Z cross sections through the image. These are now images of the 6 different Bragg peaks, imaged separately by the inversion method that we use, and these are cross-sectional images of the pattern of strain inside, using unfortunately a different color scheme from the one I used before. And you can see that there is quite a rich distribution of strain inside there. And what Marcus was able to do then is to combine all of these together, because we've now got six different projections of the displacement field, which is a 3-dimensional vector. So we did a least squares fit on every pixel to the displacement field, and so it was able to get a 3-dimensional image of the displacement field mapped out inside this front-sized zinc oxide nanowire. And you can then take the derivative of that, and so the formal strain is actually this tensorial quantity here, which has got 6 components, and you can see the 6 components are all clearly different from each other, but they tend to be strongest at the 2 ends of the wire. One end is the end where it's attached to the substrate, and the other end is the free end. We don't actually know which is which, but we do get a consistent picture that some of the components of the strain tensor are peaked up at the place where it's contacting presumably where it's contacting the substrate. You also get not showing it, so we'll just move on. Okay, so the next thing I'm going to talk about is imaging of lattice defects. This is also relevant if you've got damaged material, and one example of a lattice defect might be what Gabriel was talking about this morning, where you put if you, for instance, put a bismuth atom into a silicon lattice, and the bismuth atom is slightly larger than the silicon atom, and it leads to a strain field around it. And in principle, one could zoom in and image that strain field and look at any anisotropies of the elasticity of the material that would correspond to that. We're not quite at the level where we can see single dopant defects, but we can see more extended defects, as you'll see. Okay, so one example would be what you get with twinning. So if you have a tetragonal crystal structure, then you can have 2 directions of the tetragonal distortion. And if you look at a fault that would occur where the two domains meet, you would have a twinning phenomenon taking place. And the way you would see it would be, in traditional diffraction, you would see splitting of the Bragg peaks in the direction along which the twinning axis is occurring. And if you do this coherently, you get an image of the whole thing. But what you have is displacements which get stronger as you get away from the twinning axis, and so you can map this onto a complicated strain field, and what you would expect to see is a pattern. I've got an example to show where you can see what the expected diffraction pattern would look like. So we've been looking for examples of this. It's not a very good one, but this is the best example that we've been able to come up with. This is a PCMO crystal, not a semiconductor material, but this is praseodymium, calcium, and magnesium oxide, manganese oxide, excuse me. It's got one of these tetragonal distortions with twinning, and you can see, we've seen several examples of split Bragg peaks. We haven't been able to image the domains that correspond to this, because this corresponds to much more than 2 pi phase shifts, and so we've not been able to invert the diffraction patterns, but we've at least been able to see a couple of examples of them. This is the the calculation that goes with the image I showed before, and you should expect to see two Bragg peaks and a set of fringes that would be tied to those two Bragg peaks. And if it's as simple as just a block of material with a twinning plane down the middle and two oppositely distorted regions of tetragonal crystal outside it, you would get a symmetrically split Bragg peak like this. But our case is much more complicated than this, and you can't really tell. Another example of defects that we've been able to isolate. This is metals again, I'm afraid, but it illustrates the point. This is Laurent Batra's work. What he learned to do was to use lithography to print triangular regions of gold onto a substrate and crystallize them into single crystals of gold. I'm not sure it's related to this lithography-based method, but we're able to do three-dimensional imaging of the strain fields inside these crystals as well, because we can space the printed gold blocks far enough apart that we can be sure that we can hit just a single one with the X-ray beam. And these are the kind of images that are coming out. We see quite often these planar defects where we're seeing missing pieces of crystal where there's the missing piece is reversed in its stacking sequence and so has its Bragg peak at a different location. And if we go to that other location, we can insert the missing piece of the crystal. So we're seeing stacking faults quite nicely in these gold crystals. Here is a pair of stacking faults that completely isolates the top and the bottom of the crystal, and there's a big slab of missing crystal which is rotated 60 degrees away. So if you look carefully, you can see on the bottom image here, this is the one where he's measured, I think, I don't remember exactly how many Bragg peaks, but let's say 3 Bragg peaks from the same crystal, which allows you to get 3 different components of the displacement field. And if you look carefully, you can see the displacements tend to line the region next to the stacking fault. So there is a strain associated with that stacking, that missing piece of material associated with the 2 stacking faults that lead to this gap in the shape of the crystal. And there's also something on the end that might be a surface deformation effect, where there's a strong concentration of strain that's appearing over there. But this is vectorial displacement measurements that have just been shown on the surface, because it's a 3-dimensional vector field that we've got, and there's a lot of information in it, but you can see the highlights of it here. So we get a lot of information about the gory details of the stacking faults themselves. And the third example is, and I'll show this a little bit later, but this just shows what we're expecting to see. But if you have a dislocation loop where you have a screw dislocation coming out of the plane on this side and going into the plane on that side due to the presence of a missing plane of atoms in the center, or an inserted plane of atoms in the center, then you get a very clear dumbbell-shaped diffraction pattern, which has got a phase of pi on one side and minus pi on the other side, that corresponds to the presence of an extra plane of atoms which is inserted and associated with the dislocation loop. Yeah, I do have an example. So this is showing, this is a gold crystal, but if you section the crystal, you find that there's just one isolated dislocation loop somewhere in the center of this crystal, and you can see very nicely the pattern of this dumbbell-shaped strain field that goes with it. And that's working rather nicely. And then finally, in the dislocation collection, here are some calcite crystals that we've looked at in the collaboration with Leeds University. These are relevant to biomineralization, but you can see that we've got screw dislocations here. This is a movie, so I can hopefully play it. Well, it played in the coffee break. So what Jesse has done to project this is he's faded out the block of the crystal itself and enhanced he's located the dislocation line. This is a screw dislocation that's going through the crystal. He's located the line, drawn a circle around it, and shown the phase on the surface of that cylindrical tube that is surrounding the dislocation. And if you look at it closely, and I'll have to play the movie again, you'll see that the phase wraps around by 2 pi as you go around that loop. So we've got a classical screw dislocation. You can see the cut plane of the wrapping of the projection of the phase just on the outside there. This particular crystal, there's another picture of it here, which is also a movie, has 3 screw dislocations in it, all pointing towards the 001 axis. So the planes that are generated by the screw dislocations are 104 planes, and they meet, the 3 dislocations meet at the 001 axis. And so this is a nice way to image them using the coherent diffraction method. So if anybody has any screw dislocations in their pocket, please get in touch, because we would love to look at some more of those. Are there any questions at this point? I'm going to start moving on to the SOI materials next, and that would be perhaps a little bit more relevant to the semiconductor type applications. All right, so this is what we're looking for. We're using SOI, particularly strained SOI. We can adapt the band structure for improving the mobility of the carriers. And we've worked out a method. Actually, this, I guess, is an industry standard method, but by collaborating with a group in Germany, we were able to get hold of some strained SOI. And what's done here is that you start with a silicon wafer. You grow a sacrificial layer of silicon germanium with defects in it, which is then thick enough that it's fully relaxed to the silicon germanium lattice constant, which is larger than silicon. And then when you grow an epitaxial layer of silicon on top of it, shown here, then you get the tensile strain in the silicon layer that is desirable for the improved mobility of the silicon in that layer. And then you implant it with hydrogen ions to generate a fracture plane, so that when you then bond it to a handle, you can then break it and transfer the strained silicon onto. Sorry, you turn it over here, as shown by the upside down writing, and then you can exfoliate and remove the damaged layer, which is this red implanted line inside this. It's called, Soitec calls it smart cut, and there's probably other trade names for this method of creating of wafer bonding. And this is one of the standard ways of making SOI, but it also works for strained silicon on insulator. Okay, so you then polish off the remaining silicon germanium, and you're left with a nice thin layer of strained silicon on top of an oxide layer on top of the substrate, and that's your wafer then for subsequent processing with the strained silicon layer inside it. So we ask the question, if we take this material and then start patterning it, then are we going to see relaxations of the pattern of strain that's put inside it? So this shows the method developed to actually write patterns onto the wafer, and using lift-off methods and reactive ion etching, we can generate a pattern structure of strained silicon on insulator, which is the thing we looked at in the X-ray beam. The collaborators are here, Usama and Manfred in MPI Halle, were the ones that did the wafer bonding and the lithography. So what we made were little squares of strained silicon on insulator. There are markers so that we can find them. Here is a SDM picture of a square, and you can see it's a 1 micron square. and the cross-section is relatively flat on top at the level of SDN. And so this is, we then took these and looked at this squared structure with X-rays, and you can see, if I can play it. So we get a sequence as we go through the rocking curve of the distorted Bragg peak. This is the strained silicon Bragg peak, which is separate from the Bragg peak of the substrate. You get a sequence of, if you look at that carefully, you can see that there's an envelope to it, and there's fine fringes surrounding that envelope. And here on the right is a sort of isosurface extraction of the diffraction pattern of that strained silicon square. So then you feed it to the algorithm, and out comes an image, and it looks like a square. Here is the CDI image of that piece of strained silicon that has been patterned onto the substrate, and the shape is a little bit ragged because the signal is fairly low, and so we get a bit of noise present. But there's a clear pattern of strain that's inside that structure, and you can see one edge of the crystal is going in the red direction, the other edge is going in the blue direction. And if we take a line through it, you can see that there's a clear relaxation of the silicon at one end and at the other end in opposite directions. And the fit is just to a straight exponential. And I noticed in Connell's talk just before that I think you had a cosh function as the expected function for this, and so it will be exponential in the two ends if I'm correct. And the decay length is 50 nanometers for this. So we've got a measure of the decay of the relaxation of the strain pattern at the edge of this slab, quite nicely measured. There's obviously some rippling going on inside the material as well, but that probably is imperfections of the strained silicon layer, which I'll say more about that. Okay, so we've got pretty good agreement with the theory, but we went a little bit further and tried to model it. And this is basically using the method that was described in the previous talk. This was Gang's work, also using the COMSOL package. And what he did was he constructed what we thought we had, which is a piece of silicon on top of a piece of SiO2 with strain present in the silicon, and you can just dial that up in COMSOL. We put in the 0.6%, which was the expected number there, and we got a result that looked very similar to what we saw. But what we found was that the decay length was wrong. So the distance was actually shorter in the simulation than it was in the measurement. And the way to fix that disagreement was to allow for the fact that the etching process probably went beyond cutting through the SSOI, but actually went a little bit into the oxide as well. And so if you build up a pedestal like this, which you could simulate relatively easily, then you could get a good fit to the curve I showed before. It's a fit from the COMSOL. Actually, I don't remember if that was just an exponential or the result from the COMSOL, but we get a good agreement with the simulation with a overcutting of about 7 nanometers that was determined here. So we've got good agreement with classical elasticity for the relaxation of this thin layer. That shows the same thing. Okay, so this is a different material, but it's the same kind of measurement done by a different group. This is Andrei Minkovich in Karlsruhe looking at wires of gallium manganese arsenide and gallium arsenide. And here he's got measurements of both the gallium arsenide peak and the gallium manganese arsenide peak. And you can see you get this very rich distribution of intensity, lots and lots of fringes. And this is an example where you have, instead of getting a single center of the bright peak, you have a distinctly spread out center. And this is the case when you have the strain bigger than 2 pi, and you have actually to do some work to be able to get this to invert. And in the case of the Minkowitz experiment, the sample was small enough that it fit entirely in the beam of the experiment, and he was able to, I won't go into the details here, but this was the algorithm that he came up with for constraining the real space, but in such a way that allowed the phase to rack, but didn't overly constrain the problem otherwise. And the reciprocal space is the same as the method that we use and everybody else uses. So he came up with an algorithm, and he was able to get images of the strain pattern that's present in the overlay of the gallium manganese arsenide, and also a complementary strain pattern in the gallium arsenide underneath. And these strain patterns match each other fairly well. So you get separate images just simply by dividing the diffraction pattern's got the 2 bright peaks, and I think you just cut it at this line here, inverted this part and inverted that part, and got 2 matching images of the 2 pieces. So that's an introduction to what we've been trying to do, and this is the last subject that I'm going to talk about. This was the thesis work of Xiaowen Shi, and she did a number of experiments on SOI, not on SSOI, so these are unstrained silicon structures, and what we did was to pattern by lithography wire structures into these so that we could look at the relaxation patterns that occurred inside those. The first thing she found, however, and this may be of interest to people in the room here, is that the SOI that we looked at, this is just a blank piece of a blank wafer of SOI that we measured. And what we found was, this is the experiment that Connell talked about, where we just put a small beam on the sample and measure the diffraction pattern of one bright peak of the SOI. And what we found was that you almost never get a single bright peak. As you scan the beam along, you get split peaks, sometimes 3 peaks, sometimes 2 peaks. What it's showing is that the SOI is actually fairly defective. And this one was just an observation of the SOI itself being relatively imperfect. So what we did then was pattern the sample. We made wires. These are quite large wires. They're 1 micron in diameter. They're 140 nanometers thick. 170 nanometers thick, and they're 15 microns long, 1 micron across. And we measure them with the X-ray beam grazing across the substrate in this direction here, and then measure a 111 bright peak off to the side. So what we're getting is we're cutting out a piece of the wire and measuring its diffraction pattern to look at the strain pattern of the piece of silicon which is inside the wire. What we found, however, was that just by looking at the repeated measurements of the same sample, there was an evolution of the diffraction pattern. And I'll show the pictures in just a moment, but this picture already here shows what's going on. The width of the diffraction pattern is increasing with time. And she looked at 3 or 4 different wires, and every one of them showed very similar behavior. So on the scale of a few hundred minutes, there is some damage taking place where the wire is becoming deformed, and getting the bright peak is getting broader and broader, and it does so in quite an interesting way. So we're seeing damage of the material. So this shows early time. You get a fairly conventional square-like diffraction pattern, just looking at the center of the 3-dimensional distribution. And then sometime later, you've now got it splitting into multiple peaks, and then it becomes bigger and bigger still. So after 240 minutes, that was the last measurement we got for this particular wire before the peak disappeared. and we've got a significant amount of strain starting to appear in the wire just by exposure to the X-ray beam. And what is going on is that it's not the wire which is becoming damaged by the X-rays, it's the oxide which is becoming damaged by the X-rays. And this is many other people have seen the same thing, that silicon oxide is actually rather unstable to X-ray exposure. In fact, the microscope image that you're looking at here, this is an optical microscope image taken during the measurements with a confocal microscope. So it's seeing the height of the sample. And obviously, the silicon wire is above the surface, but the fact that you can see where the beam has been hitting the sample means that the oxide has become increased in height by some beam-induced damage, which, in fact, we were able to demonstrate that it's related to oxygen in the air, because if we replace the air with helium, we get no damage effects. So it's presumably ozone generation by the X-ray beam attacking the substrate probably and causing a thickening of the oxide in the region where the beam is hitting it. And the interesting thing then is that the wire is sitting across this bulge of oxide and is becoming distorted by the pressure of the buildup of the oxide underneath. So we decided to study that. We've got these diffraction patterns measured at different times of the growth of the oxide. And going back to console, we were able to model these. What we did was just model what we thought was happening, which is we put a piece of silicon on top of a piece of SiO2 and then a silicon handle underneath. And inside this box region here, we put a Gaussian-shaped stress profile and increased the value of the stress that appears inside that box. And what happens is that this is the Z component, the vertical component of the distortion. The middle moves upwards and makes a sort of bridge-like picture. That's shown in red over here. That's the height of the sample for the value of the stress that we've applied. And in the sideways direction, you get a sort of dipole where it responds to the mechanical distortion of the bending of the beam with a left and right motion that's shown in the blue curve over here. So we've got predictions for the distortions of the wire, and then we can just take the Fourier transform of those and look at the expected behavior. So this is showing the distortion converted into a phase. We've assumed a Gaussian-shaped beam profile, and we've assumed that it goes right across the cross-section of the wire, and the mechanical response of the wire has got a two-dimensional redistribution of the distortions due to the antiplastic bending of this associated with this process. So these are just simulations of what is going on as a function of the peak pressure of the distortion that we put into the console calculation, running up to 450 megapascals for the highest value. And the calculated diffraction patterns look a lot like the experimental one that we saw at the largest time. So we've got this quite similar appearance of the diffraction patterns. So what Xiaowen then tried to do was to use these best guess diffraction patterns as a starting point for the phasing algorithm to actually go in and phase this diffraction pattern, which is otherwise impossible to phase. And she came up with a new method called a guided phase error reduction algorithm was the name that we finally settled on. And you can see that you get phase distributions which, this is the input phase for the reconstruction of this object. And the amplitude comes out a little bit broken up, but mostly filled in. You've got ragged edges where the edge of the beam occurs, but you've got a fairly good reconstruction of a solid piece of silicon, but the phase is actually quite rich. So what we are seeing, and some of this is noise because the data are a little bit noisy, but we're seeing at 45 minutes a relatively unstrained pattern with a little bit of strain at the edges. The strain moves in at later time and in further, and at 240 minutes, which is the last one before the diffraction pattern disappeared, we're seeing quite rich zigzag-like phase structure inside the wire. And if you zoom in on that, you can actually see, you have to look quite closely, but you can actually see in these, sorry, this is the center pattern here. You can see these dumbbell-like structures. There's quite a few of them appearing. The Q vector is in this direction here, and the dumbbells are appearing roughly in the direction of the Q vector. And those are those are signs of those dislocation loops that I talked about earlier. So there's the dislocation loop again. So if you stretch your eyes, you can see that there are phase racks occurring where you jump from blue to red. This is pi to minus pi, and they occur localized in regions where you have these little dumbbell-like features. So we think we're seeing the formation of dislocation loops due to the bending of this silicon structure, and presumably the next diffraction pattern which we didn't measure because the sample disappeared was the one where the sample broke. So 5 minutes, okay. So we're seeing mechanical deformation. We're seeing the formation of dislocation loop-like structures. Interestingly, the beam is this is about a micron long, and the width of the beam is about a micron, and it's coming roughly in this direction here. What we're seeing is relatively few dislocations in the middle of the sample, but they're occurring at the edges where the gradient of the intensity profile is highest. So that's the place where I think you would expect the fracture to take place, but we haven't confirmed that. So we're seeing roughly at the half height point of the beam is where we get the biggest number of these dislocation loops occurring. Okay, so I'm going to have to be very brief with this last topic, and I think what I'll try to do is just simply summarize what we're doing here. This was the part where I was going to talk about some of the future things we could do using X-ray free electron lasers. And we've done one experiment where we've looked at this coherent diffraction imaging method applied to gold nanocrystals. We haven't done anything with semiconductors yet because it's very hard to get time on the one hard X-ray free electron laser facility well, there's two in the world which are running, one in Japan, one at Stanford. We've been mostly working at Stanford, and we've done one experiment at Stanford, which I'll just very quickly talk about. So this is a photograph of the setup. It's got quite a lot of people involved because you need a big team you get 60 hours of beam time, and you have to not waste a minute of it, so you need a big crew. What we were looking at was pump probe excitation of a block of gold, a gold nanocrystal, and what we were expecting to see is compression waves occurring in it, because the light would be absorbed in the electromagnetic skin depth, which is about a couple of nanometers for these 9 kilovolt X-rays. So we're expecting to see a compression wave, but what we actually saw, skip over this, what we actually saw was a Bragg peak. This is the 2 theta value of the Bragg peak as a function of delay time, and this is the time delay between the excitation with the Ti-sapphire laser and the X-ray laser, which are both femtosecond long pulses separated by a time in the range of picoseconds here. And what we see is a drop of the Bragg angle of the Bragg peak of the gold, indicating that the crystal is expanding. So that picture I just showed you is incorrect. And the correct interpretation of what's going on is that when you laser excite a metal, you first of all excite the electrons, but you don't see the electrons in an X-ray diffraction experiment. What you see is the lattice, and there is a time delay between the excitation of the electrons and the coupling to the positions of the atoms inside the crystal, which is given by an electron-phonon coupling constant of some kind. And that's believed to take place on the timescale of about 1 picosecond, much less than the oscillation period that we're seeing. But more importantly, because you excite the electrons first, the electrons can travel very fast through the crystal, and you're not going to just see even though the light is absorbed inside the skin depth, the electrons travel right through the crystal, and by the time they transfer their energy to the lattice, they've already completely filled the crystal. And so we get uniform heating, as far as we know, of the crystal by the electrons that are generated by the laser hitting on one side of the crystal. And this two-temperature model is fairly well established for laser heating of metals. What happens in semiconductors is a very interesting question. We would actually like somebody to think about that. But conceivably, because of the very high temperatures of the electrons here, it's probably not going to care whether it's a metal or a semiconductor. Anyway, so we proceed to image proceed to analyze the position of the Bragg peak, which has got 2 oscillation periods in it. They correspond to vibration modes of the crystal, one in the radial direction, one in the transverse direction. And we can then look at let's skip over that, and then look at the shape of the crystal after taking out the simple breathing modes of the vibration. We can then look at the next order mode of excitation inside it, which is shown here. X, Y, we've got 3-dimensional images, compression and expansion waves. We're looking at the vibrations of the crystal measured as a function of delay time after the start of the vibration of the laser. And we get a pretty good qualitative agreement with a higher order shear mode of a cylinder, which is in some notations indicated as the 1-1 normal mode. So we can agree relatively well with the pattern of expansions and contractions with this higher order mode. So this is something that still needs to be tried with semiconductor devices one day. But this is looking into the future. Okay, here is a simulation of a heat pulse coming into a generic crystal, and you can see the waves of vibration traveling through it. And if you take that MD simulation and Fourier transform it, you get a nice oscillation of the Bragg peak position. Okay, so I'm going to stop at this point and skip forward to. Conclusion. I don't want to omit my acknowledgements. Okay, so with gang's name added this time, these are the group members that have worked on the work that I just talked about, the support from the ERC, and these various people contributed to the different sections of the work that I just mentioned. I didn't have space to put all the LCLS people down. And very importantly, we did make good use of the clean rooms that have been running for the entire length of the grant that we've had in our LCN facility for doing the lithography of the SLI samples. So thank you for your attention. I welcome questions.
It's been a long day, but we still have some time for a couple of questions.
Can I know the resolution of this X-ray laser? So we really take the stream profile in the 2 nanometer silicon FinFET?
You want to know the resolution?
Yeah, resolution.
Yeah. We're presently getting about 20 nanometers resolution for the best samples, and for less good samples it can be as bad as 50, 60, 70 nanometers. But we're never going to get TEM-like resolution. We don't want to get TEM-like resolution. My point about the protractor was that the strain fields are actually quite slow varying, and so 20 nanometers resolution gets quite a lot of information already. But that's mostly limited by flux, but as you saw in the case of the silicon, if you increase the flux much more, you start to get damage problems in some cases. So you know, it is not necessarily going to be an easy thing to improve. So I think we stick with 20 nanometers for a while anyway. Yeah.
One more?
So I was looking at the LCOS measurements that you did, of course, repeatedly shocking
Yep.
it's 1 nanocrystal.
1 nanocrystal.
Which is repeated. How many, what's the yield here on this experiment? I mean, how many nanocrystals did you fry before you got one that good?
Well, you fry some to calibrate the lasers, right? So both the optical laser and the X-ray laser were turned down from their maximum flux. So in the case of the X-ray laser, about a factor of 10, because it was already focused, and the focused beam, nothing survives. So we had to attenuate that by about a factor of 10. And also the optical laser, we had to attenuate that with just burn holes in the sample as well. So we're working below the threshold for both lasers, which is experimentally determined. So you sacrifice a lot of crystals learning what those levels are. But once you get below the level that the sample survives, it survives for many hours. So you can do
1 nanocrystal.
One nanocrystal survives for many hours.
How did you? I mean, it's on a conducting substrate or insulating substrate?
It's insulating nominally, but who knows with the sort of excitations that are around. So you're concerned about charging.
Well, I mean, obviously things are more susceptible to damage.
That's all for the future, but I'm sure that there will be ways of making samples that are more radiation safe and improving the experiment.
How was it mounted?
These were mounted on SiO2, so the gold was prepared. It's actually the method I mentioned with the patterning, where you can use a thin gold film and heat it in a furnace, and you get de-wetting into individual crystals, and you get millions of them, so you've got plenty to burn up on. And then you just find a nice one that's pointing in the right direction, that's free from lots of neighbors, and you know, you can, once it's stable for 2 shots, it's probably stable for a few hours, but that was the experimental approach that we took.
Okay, let's thank Ying and all our speakers for today. We will reconvene tomorrow morning at 9 o'clock, according to this schedule. Thank you very much.